Hey everyone, in this video lecture we're going to discuss various enhancements to PID feedback control loops. The content of this lecture comes from Chapter 13 of Chemical and Bioprocess Control, the 4th edition by James Riggs. So in this lecture we're going to discuss four main types of enhancements. The first one is called Inferential Control. So your objective for inferential control is to discuss different ways that you can use inferential control to improve the performance of feedback control loops. And we'll do this through various lectures, or through various examples. The second thing that we're going to discuss is called controller scheduling. So controller scheduling is essentially setting different parameters for PID based on a specific process measurement. The third thing we're going to look at is OverrideSelect Control. So OverrideSelect Control is an important PID feedback control design strategy that's used to incorporate or used to make sure the process doesn't go outside of process constraints or safety constraints. And the fourth topic is computed manipulative variable. And the idea of computed manipulative variable, or the use of computed manipulative variable, is necessary when a single measurement can't be used in order to change the manipulative variable to achieve the desired control necessary. Okay, so in this lecture we're going to go over the general theory and strategies, and next time we're going to do various examples of implementing these. And specifically, next time we'll really focus on designing different types of override select type systems, and we'll look at some examples of inferential control and computed manipulative variable. All right, so first, there are various limitations to PID controllers, and some of the performance can be limited substantially by measurement lag or dead time. Other types of ways processes can be limited are based on nonlinearity. And again, what nonlinearity means is that the values of the PID controller parameters, the gain, reset time, or derivative time constant, are different, or the optimal value, or the optimal parameters are different depending on the current state at which your system is operating. For example, if it's operating at an incoming flow of 5 gallons per minute versus 10 gallons per minute, how your system responds to changes in disturbances can vary depending on how your system is currently operating. And then finally, we have process constraints. And process constraints can be things like physical limitations, like tanks emptying, or they can be safety constraints, like systems becoming too hot, or tubes fail, or reactors are on the verge of thermal runaway. So here we'll look at clever use of process knowledge and control logic to circumvent some of these types of systems. Okay, so inferential control, this is going to be our first topic. So inferential control, the idea of inferential control is to use an easily measured process variable. So the things that are easy to measure are temperature, pressure, and flow. These can be measured typically pretty quick, very accurately, and the control systems are fairly cheap. So inferential control is to use these process variables to infer more difficult to measure quantities. Difficult to measure quantities might be composition and molecular weight. So composition oftentimes require a sampling system, and sampling systems can take multiple seconds, minutes, or hours to correct a measurement data. What we know based on our material balance and energy balances for reactors is oftentimes the composition is equivalent to the temperature of the system. Also for distillation columns and things like that, we can correlate those things. For polymer systems, maybe the pressure flow is proportional to molecular weights, and we can correlate these types of parameters, which are what we care about in terms of determining the value of our product. We can determine these parameters based on measurements of temperature, pressure, and flow. So this can be used to substantially reduce dead time, because again, dead time often comes from measurement of composition and sampling systems, and lag. So lag between when the disturbance affects the process, when we see a change in our control variable, and how long it takes the controller to reject that disturbance and get our system back to the desired set point. In this approach, also the use of inferential control can reduce both your capital and your operating expenses. Why is this? Oftentimes because temperature and pressure and flow sensors are much cheaper than composition sensors or molecular weight sensors, and operating costs, again, because systems don't have to be sampled, the cost of taking these types of measurements is often higher than the easy to measure things like temperature and pressure. Oftentimes inferential control is necessary because the measurements can't be achieved any other way. So let's look at an example of the effect of dead time on the control performance. So this system right here shows your control variable response. So this right here would be our control variable response. For example, this could be something like either temperature, maybe, or composition, etc. as a function of time. So for systems that have a long lag time, if we tune our controller for the proper tuning criteria, and let's just say in this case, our tuning criteria is a decay ratio equal to 1/5. Right, so if we tune our controller for a decay ratio of 1/5, when our system has a lag time of, or a dead time of about 1.5, and this is arbitrary units, it could be minutes, hours, you can see for the same sort of decay ratio of 1/5, the error between the set point, so this step right here, can be our y specified, and this response is our y sense value. So we can see in this case right here, there's a lot of error between our control variable and our set point. In the case where the dead time is smaller, for the same type of decay ratio, we can see here, based on the decrease in the second peak to valley over the first, now here our error is significantly reduced. So the response, it gets to the new set point much faster, and then the error associated with each of the individual loops becomes significantly reduced, and the system settles in the new value much quicker than before. You can achieve this type of performance by simply replacing, if you simply replace a composition sensor with a temperature sensor. Because again, the temperature sensor might take a couple minutes to get the composition value, and the temperature sensor is going to be significantly faster. In this type of approach, it's still necessary to measure the composition periodically to make sure that the composition is at the target value. Inferential control is an important, or it's a standard practice. It's used on distillation columns. In distillation columns, it's not necessarily practical or cost effective to determine the composition. So ideally, if you were going to measure the composition, we could have a composition sensor, a composition controller. Let's just say we want 3% impurities concentration as our set point. This could perhaps be either cascaded to the flow or cascaded to the temperature sensor or temperature controller, which is cascaded to the flow. We talked about these things previously. Because of the lag time associated with this, so we have a lot of lag associated with collecting this measurement, we can bypass this by correlating the composition with the temperature of the distillation column. So now in this case, we would have T specified. And in this case, we can make the measurement and the system can respond and have the steam flow change much faster. When you do inferential control on a given process, it's really important to think about where you're going to incorporate the inferential control. So the temperature as a function of composition. So T is, let's just say F10 for tray 10 as a function of composition for this column. So T of tray 10, and let's call this tray 18. So the temperature of tray 18 is now a different function of composition. So what we want to do for inferential control is we want to have we want to have a system that has a strong correlation with composition so that we can maintain accurate control. So here's what I mean by that. So this composition right here, let me specify this. So this would be the composition coming out. We know we can measure the temperature dependence of the composition for both of these trays, or we can even do it for other trays too, and determine what would be the best temperature to use to infer the composition coming out. Okay, if we look at this slide right here, this slide shows that the function of, or the temperature dependence of composition in the product on tray 18 does not vary very much with composition. So as the composition changes from 3 to 5, we don't see a very strong correlation. And this is in fact probably within the noise of the sensor. Whereas for tray 10, we can see there is a much stronger composition between, or much stronger correlation between the composition of the product stream and the temperature of the column. So we would use the temperature of tray 10 to infer composition. So this is a better use for composition because it has a stronger dependence on the temperature has a stronger dependence, or the composition has a stronger dependence on the tray temperature. Okay, we can use inferential control for reactors. Okay, so if we look at our balances on here, we know that for we're gonna call this a continuous stir tank type reactor. So we're just gonna assume that for this case right here. Based on the material balance, we can come up with a relationship between composition and temperature based on what we've learned in our previous classes. Okay, if we use our general material balance for this system, we'll consider the reaction of A goes to B. Simple reaction, stoichiometric equivalence. We know that from our material balance, the mole balance, the flow of A in, or FA naught minus FA plus RAV equals 0. We also know that FB0 minus FB plus RBV equals 0. There's no B coming in, so this term is 0. And then we also know from the reaction is that RA equals negative RB. Okay? So we have this as our material balances. We can also write these in terms of conversion, so we can define conversion X. So our conversion, a reaction conversion, equals FA naught minus FA over FA naught. So in other words, FA naught minus FA equals FA naught X. So we can write this as, from this relationship right here, we can say negative RAV equals FA naught minus FA, or FAO minus FA, as shown up here, equals FAOX. Okay, so we also have our energy balance for the system. So our energy balance on the reactor, we have the flow coming in times the enthalpy coming in. So FAO HAO minus the flow of species coming out. So coming in, we have species A. Coming out, we have species A and B. We're going to call this adiabatic. And we're going to say no shaft work. Okay, so only A coming in, so flow of A. And again, based on the temperature coming in, the stuff coming out is we have FA times the enthalpy of the stuff coming out minus the flow of B times this enthalpy of B coming out. So we have energy due to flow coming in minus energy due to flow going out, plus the amount of heat that's done. Since it's adiabatic, this is 0, plus shaft work, we said this is 0, equals accumulation. Since it's a flow system at steady state, our accumulation term is also equal to 0. Okay, so here's our energy balance on the system. We can do some substitutions here. Okay, so we have our material balance and our energy balance. If we put these two things together, we can come up with a correlation that relates conversion with temperature. Okay, so let's do that. Let's see, so for this term, we can replace, what do we want to do? We want to replace FA, this term right here. We can say FA equals FA naught minus, or we'll use this term right here. We're going to take this term right here and solve for FA. So if we solve this for FA, we have FA equals FA naught plus RAV. Okay, so we'll put that into here. So we have FA naught, HA naught minus, in for this term right here, we're going to put this relationship. So this is going to give us FA naught times HA minus RAV times HA. Okay, since since FB equals RBV, this is going to be negative RBV here. Again, we know that RBV equals negative RAV equals negative RBV, so that we can replace negative RB with this term right here. We're just going to call this plus RAV times HB. Okay, so now we can rearrange these terms a little bit. We can do a little bit of math. So this first term, HA naught minus HA, this is just a delta H term, and we know that delta H equals CP delta T. So this first term is going to become FAO CPA times T0 minus T. And now this term over here, we're going to factor out a negative R, or we're going to factor out plus RAV, and then this is going to give us HB minus HA equals 0. Okay, so now this term right here is going to be our heat of reaction term. This term right here is our sensible heat term. So now from this relationship right here, we have negative RAV times the heat of reaction, right? And this is the heat of reaction at T, equals FAO times CP heat capacity of A times T naught minus T. So finally now, we can get our temperature dependence because we know that this term RAV equals FAOX, so I can replace this term right here. We have FAOX times the heat of reaction. So FAOX times heat of reaction at T equals FAO CPA T naught minus T. In this case right here, now we can go ahead and divide through FA naught cancels off. We can divide through by here, and then we have XA equals, I'm going to take the negative of both sides, so we'll have CPA divided by negative heat of reaction T minus T naught. And I like to do it in this way because for exothermic reactions, right, this term right here becomes a positive term. And so we know for a exothermic reaction, T is going to be greater than T naught as the conversion goes from 0 to 1. Okay, I just like to use this sign convention. But overall, we look at this right here, and the important point is that theoretically, this is what the relationship would be. In practice, we can just say that X equals some constant A times T, maybe plus or minus B, which is another constant. And what we can do is we can make measurements to come up with a correlation between X and T, because again, you know, this is theoretically what the relationship is going to be. We can make some measurements in practice, and the correlation that we make based on the measurement is going to be a better measure to use for the inferential control for this reactor system. Okay, This right here is in addition to looking at inferential control, I like this example because it shows us how to incorporate our basic material balances, our basic energy balances, combine these together and see what the type of dependence is going to be of one parameter on another parameter. And this is an important tool that you should be able to do as a chemical engineer. And this is something that you can use in your practice because it's nice to know, is the conversion a 1/2 dependence? Is it linear? Is it square root, power law, etc.? You can do this by understanding the basic material and energy balances for your systems. All right, let's move on. Another system that we can use for inferential control is that for the molecular weight of a polymer. So it takes a long time to measure the molecular weight of the polymer. You can use gel permeation chromatography, and maybe it takes on the order of 20 to 30 minutes to get a good measure of the molecular weight. You don't have this luxury in polymer processing, so we know the correlation between different terms for the polymer. And importantly, polymer physics tells us that the molecular weight of the polymer is a function of the viscosity of the polymer at a certain temperature. So by knowing the viscosity of a polymer at a certain temperature, we can know the molecular weight. Okay, again, viscosity might be a tough parameter to measure. We can measure it, it just takes time. We also know that the viscosity at a temperature, we know the viscosity has a temperature dependence, so it's important to know the temperature to know what the viscosity is. And then finally, we're kind of working back up, we know that the viscosity at a specific temperature is a function of the pressure drop in the flow. So by knowing the flow rate through this extruder reactor and the pressure drop from the entrance to the exit, we can get the molecular weight. And pressure drop measurements are fairly quick and straightforward. Flow measurements also quick and straightforward. We can use these two measurements to infer the molecular weight of the polymer. Now remember, as you're doing this, at least every couple hours or every day, you're probably going to make measurements of the polymer and take corrective actions or refine your inferential control correlation, etc., to maintain your molecular weight where you need it to be in order to sell your product at the right value. All right, next method or next strategy to improve PID control is called adaptive controller tuning. This can also be called scheduling. And so the important thing is this is really necessary when our system is very nonlinear and subject to large disturbances. So when our system is nonlinear, what this means is that the effective when measured disturbances or the control variable correlates well with nonlinear process changes. Okay, and we'll go through a couple of examples from this. But the important thing to know is that if your controller performance varies significantly depending on what your entrance conditions are, for example, flow rate or temperature, then you may need to have a different set of controller parameters, either the gain reset time or your online tuning factor, depending on a measurement of an incoming process parameter. So the strategy, like I said, correlate the optimal controller tuning parameters. So we'll have a different set of controller tuning parameters with a predictive process variable. All right, so we'll discuss what that means on the next slide. Okay, so here's an example of a heat exchanger. And the heat exchanger performance is nonlinear with respect to incoming flow rate. So as this feed flow changes, the optimal value of the gain reset time and derivative time constant for the PID controller are going to vary. Right? So shown here is the process control diagram for the heat exchanger. Right? What we're missing here is we're missing a specified value on the temperature. Okay, so for this heat exchanger, we have the feed flow coming in, measuring the coming out, we're measuring the feed coming out, and we're going to vary the steam pressure to achieve the heating that we need to keep this at our specified value. We'll have condensate, the steam will condense and come out as condensate. If we look at the performance of the system, so we measure what y-axis is the change in temperature, delta T, in response. So this is delta T in response to a step change in, for example, steam pressure. So a step change in P steam. So we're manually changing the pressure or the valve position on the steam, and we're looking how the process responds. Okay, so if the flow rate of the system is 4 feet per second, our process, we see there's a little bit of lag, and then we'll see the process. The gain is fairly high. If this system is flowing at, for example, 10 feet per second, we can see maybe the process levels out a little bit faster, but the gain is significantly smaller. Because these gains are very, very different, maybe the time constants also vary a little bit. Because these are very different, the PID controller parameters are going to, the required PID parameters are going to change. Remember what we did before is that when we looked at some of the classical, tuning strategies, we could say that, we can fit these, when we fit our model data to first order plus dead time model, the PID parameters were heavily dependent upon what these values were. Okay, so because of this, the controller is going to behave much different depending on what the entering flow is. So in order to compensate for this, we can, a lot of controllers can have what's called a scheduling feature or adaptive controller feature. And what that means is that a certain measurement is made. So for example, we might have a measurement of flow. And so for a certain measurement of flow, we'll have a value of Kc, tau I, and tau D. So maybe we'll have a flow range of 2 to 4. We have a certain numbers. For a flow rate of 5 to 7, we have a different set of parameters. And then for 8 to 10 or above, we'll have a different set of parameters. And what this will do is this allows us to vary the settings based on the measurement of flow to achieve the performance that we need. Again, this is important if two things occur. Our process is nonlinear. So if our process is nonlinear, we might need to do something like this, and also subject to large disturbances. So a process that's nonlinear and subject to large disturbances can become unreliable, like we saw in a previous lecture. In order to maintain reliability for a nonlinear process that's subject to large disturbances, it's required to use this type of adaptive controller scheduling approach. All right, the next strategy we're going to look at is called OverrideSelect Control. Okay, so we're going to discuss this through a few examples. So OverrideSelect Control is a strategy of incorporating feedback control loops to maintain your process near a safety-related set point or prevent your process from getting to certain constraints. So here we're going to go through a few examples to discuss the implementation and operation of OverrideSelect Control. Next time, we'll spend most of the time going over some examples. So I'd look at some of the homework problems that are related to OverrideSelect beforehand and see what you can do in terms of incorporating the different types of control loops based on what we discuss here. Okay, so again, this is important because processes often operate near a safety-related or equipment limit, and we want to prevent the system from going over those limits. And the safety systems must be enforced so that the overrides take precedence over the normal control action. So I'm going to summarize here a little bit what we're going to do. In most cases, when we have OverrideSelect Control, we have two independent control loops that try to change the manipulative variable. The OverrideSelect Control is going to select one of these control loops to control the manipulative variable. During normal operation, when you're below the safety limit or the process constraint, the select controller should operate such that it's selecting the primary objective, which is the economic objective. We'll call that our main control loop. When the system gets close to the safety-related loop or the constraint loop then takes over and keeps the process from going over the constraint. And this is done by having a loop that keeps the process operating at that safety constraint or at that process constraint. So we'll show this by example on the next slide. Okay, so here's an example of a level select control on a furnace tube temperature constraint. And I'm going to do this example by first describing how the system is implemented and how it operates. And then we'll look at the same exact example and we'll discuss how to incorporate the loop. Okay, so we'll start by how the operation occurs. Let's think about this system. Let's start by looking at how it's operating. So we have a process fluid that's going through a furnace, and the primary control objective is we want the process fluid, we're heating it up, so we want to have it at a certain temperature. So our primary control loop is we have a temperature controller that has a specified value. Okay, and for now, without any sort of override control or override select control, this system would, the temperature controller would change the flow of fuel that's going into the furnace to keep our process fluid at the target or specified value. This system has the fuel feed set up as a cascade control. So we have the temperature of the process fluid controller is cascaded to a flow controller on the fuel. Okay, so we talked about cascade control before. So this is our cascade loop. So cascade is used to minimize the effect of a specific disturbance. So the specific disturbance from here would be related to the fuel flow. So perhaps a change in pressure, upstream or downstream from the flow from the fuel can affect the flow through this valve without anything else changing in the system. Okay, one of the things that can happen in the system is if the temperature of this of their product decreases, the primary control loop is going to ask for more and more fuel. As more and more fuel is fed to the furnace, the temperature of the furnace is going to heat up. And the temperature of the furnace, the temperature of these tubes can get hot. And if the temperature of the tubes can get too hot, it can either cause wear or potential safety dangers associated with these tubes failing. To prevent these tubes from failing, we're going to incorporate another control loop. Okay, so we did our primary control loop. We already did that one. So separately, let's think about how to design a temperature control loop for the temperature of these tubes. Okay, so we want to keep the temperature from getting too hot. So what we're going to do is we're going to measure the temperature. Okay, so for the control, we need to measure the temperature of these tubes. Then we need a controller for this temperature. Okay, so here's our temperature controller. So we're measuring this, and then we also need a set point. We'll talk about what this set point is going to be. Okay, so the temperature of these tubes is going to be changed by changing the fuel that's fed to this furnace. So by changing the fuel, it's going to affect the temperature of these tubes. So again, this system right here would go to the same manipulative variable. Okay, but we don't want both of these. We don't want both of the signals going to the valve. We only want one signal going to the valve. Okay, and the signal that we want going to the valve is going to be we want it to be mainly this signal, but if the temperatures are at the constraint, we want it to be this signal. Okay, so the way that this is implemented, let's go ahead and erase this line right here and this line right here. Okay, so our set point for our constraint loop, okay, this is important. The set point that we use for our constraint loop is the set point of the safety constraint or the process constraint. So let's just say the safety constraint of this one is the temperature of the tubes, maybe 800 Fahrenheit. So our set point for our temperature control loop, 800 F, is our set point. This controller is going to ask for a flow rate to get us to 800 Fahrenheit. So our process constraint loop, the purpose of that loop is to put us at our set point. So if we're below it, we're trying to get up to the set point. If we're above it, we're trying to get down to the set point. That's the objective of the process constraint loop. This seems a little bit counterintuitive, but trust me, this is how we design our select control loops. Okay, so for the normal control loop, that's the same. It's going to go to the level set controller, it's going to go to the select controller. This right here says L, which looks like a low select, but we haven't decided that yet. So both of these signals are going to go to a select controller, and the controller is going to send one of those signals forward. So one of the two signals of either the process constraint or the economic objective loop is going to be sent forward to control the furnace fuel feed rate. Okay, so we're selecting. So now how do we select? We either going to select the signal. One of these signals is going to be higher than the other one, right? So this loop right here is asking for a flow rate that's going to get these tubes operating at the maximum possible temperature. What do you think that is? High flow rate or a low flow rate relative to the economic objective, right? It's going to be high. So this signal right here, relatively speaking, is going to be a high flow rate. So this is going to be essentially, or another way you can think about it is this is the maximum possible flow rate that this fuel can be in order to keep this below the set point, right? So relatively, this would be a lower flow rate. So under normal operation, if this is at 400 degrees F, for example, this over here is going to be a low flow relative to the other set point. What that means is that the flow, if this is operating at 400 degrees C, we can send in a much higher flow rate of fuel as we need to get this, to keep this temperature at our specified temperature value, right? Under those conditions, when this is operating under safety constraints, the process constraint is trying to get us to our maximum set point, which is 800. And so this is going to be a high flow. Therefore, because this relative to normal operation, when this is operating safely, this is a high flow relative to this, so we need a low select. Okay, let's discuss operation another way. Now I'm just going to throw some values on here. Maybe this is coming in at 25 degrees C and we're preheating it to 100 degrees C to go into a reactor. Okay, everything's operating normal. We're at 400 degrees C. Now let's assume, this is operating at a flow rate of, 5 gallons per minute. Let's assume at some amount of time we need a higher flow rate going into the system because of what's going on elsewhere in the process, and we need to double this to 10 gallons per minute. As this flow rate of the process fuel increases, right, the temperature is going to decrease. Therefore, this temperature controller is going to ask for more heating. Okay, the flow of fuel coming in is going to increase. This is going to go up to 500, then 600. Again, as we need to continue to increase the flow of fuel, this is going to increase. As this signal increases, right, now the difference between the set point here and the set point here becomes lower. So this signal right here initially was really high. Now it's just a little bit higher than the signal. As this gets up to 700, this gets up to 700. Once this gets to 800 Fahrenheit, right, let's just assume now this is at 10 gallons per minute, this is at 100 degrees coming out, and now these tubes are 800 Fahrenheit. When this is at 800 Fahrenheit and this is at 800 Fahrenheit, the error here is 0. If this is at 100 and this is at 100, the error is 0 here. These two have the same signal. The valve position now is at a maximum. If this flow rate continues to increase and then the temperature here drops below 100, let's say it drops down to 95, now these tubes are at 800. Okay, the error here, this is at its set point, and now this signal right here, the signal from this controller wants a higher fuel flow rate. So this signal is now asking for a higher flow rate coming in, but because this is a low select controller, it's going to send the zero change signal, which is lower than the signal here. Okay, so let's reiterate a couple things. Under normal operating conditions, right, when this is at the set point and this is below the maximum value, the signal of the economic objective is lower than that of the process constraint because the select control or the process control constraint or the safety constraint loop is asking us to get us to our constraint. Okay, so this signal right here would be lower than this signal. this would be at the temperature would be at the specified value, and the flow rate of fuel would be below the maximum flow rate of fuel allowed for the system. Once we get to our safety constraint, once we're at 800 degrees, and this is now below the specified value, the temperature would be below the specified value, the temperature of the tubes would be at the safety constraint, and the flow rate of the flow of fuel would be at the maximum flow of fuel to keep us at this specified condition. Okay, so overall, that gives us a really comprehensive discussion of override select. All right, we might have to apply this to we will apply this to various types of systems, and there are a variety of examples that you need to do. But this is going to be an extremely important concept that can be used for feedback control, for your career, and for our next exam, or next couple exams. Okay, so we can summarize on this next slide. Again, this says under normal conditions, the controller adjusts the furnace firing rate to maintain the process stream at the set point temperature. Okay, we showed that. At higher fuel flow rates, high tube temperatures can cause tube failure or reduction in useful tube life. So the low select controller, it selects the process stream set point at normal conditions, but here we can, I want to write this as summary. So the process side, we'll say if the process side asks for too high of fuel flow, if the process side is asking for too high a fuel flow rate that will put us over that safety constraint, the safety side takes over. Right. In other words, the process is at its constraint, and now the safety side will have a lower set point to the flow controller than the process stream set point side. Therefore, the lower select controller will run based on the safety constraint side. And again, that side will be keeping the tubes at their maximum temperature value. Make a comment here. In general, if the safety constraint is a maximum, a lower select controller is probably what you're going to use. If the safety constraint is a minimum, it's probably going to be a high select. But that's not really always true, and that's going to be a common mistake that people make. What it depends on is what is the value of the manipulated variable. So does the value of the manipulated variable need to be a maximum to keep it at the process constraint, or does it need to be a minimum to keep it at a process constraint? A good example to look at for this would be maintaining or preventing a tank from overfilling using the flow control at the inlet versus the flow control at the outlet. Because again, to prevent the tank from overfilling, you would have a different value to the manipulated variable if you were controlling it based on the inlet stream versus at the outlet stream. Okay, so let me say that again. If your constraint is a maximum or a minimum, that doesn't tell you whether you want a low select or a high select controller. What you can use to determine whether or not you want a low select or a high select controller is the value of the manipulated variable to keep you at your process constraint or your safety constraint. Okay, so we can do an example column flooding constraint. So in this case, we want to reduce the stream when the pressure drop in the column gets too high. Okay, so let's kind of see how this system would be implemented. Okay. In this case right here, we're going to ignore this side for now. And so we have a distillation column. In the distillation column, we want to keep the product at a specified value. So we have a set point of the composition, measure the composition. This composition controller is going to set a remote set point for the flow of steam. We're heating the boiler in the column using steam. We have measurement of the flow of steam. So based on the measurement of the flow of steam, the controller is going to open or control this valve to keep a target steam or to keep a target heating rate. What we know though is that if the pressure drop in the column gets too high, the column can flood. So we want to keep the column from flooding. In order to keep the column from flooding, we need to incorporate a select control in the system. Okay, so how do we do that? We need to measure. So we need to measure pressure, or dP, the delta pressure in the column. So we measure the pressure in the column. We have a pressure controller, and our set point is going to be maximum pressure. That's our operating constraint, maximum pressure. So maximum pressure, and measure the pressure. We have a maximum, we'll call this delta P, max delta P. This goes to the flow control valve. So what this is going to do is this is going to ask max flow. So this is going to ask for the maximum flow of steam to get us to the delta P max. So because our signal is a max flow, that means we want a lower select control. So our safety constraint loop and our economic loop are going to go to this low select controller shown here. This is going to go here. During normal operations, this signal will be low because the delta P will be lower than necessary. If the composition gets out of spec and it's asking for too much heating on the system where the column is about ready to flood, the safety constraint / operating constraint loop will take over and will keep us at that maximum pressure, and then the composition loop will become out of spec for the system. Okay, the last system I want you to think about is I want you to think about a system that would have some sort of level control, like maybe an accumulator on a distillation column or something, and your override loop would be to prevent the level from either overfilling or emptying. Come up with a system where you can show that you would need a high select control or a low select control, depending on whether or not your control is based on the inlet flow or the outlet flow. That's another good example to think about. I'm kind of giving you a hint because that example is going to show up later. All right, so let's summarize our override select control. And then next time we'll go over some, again, other types of applications. Okay, so override select control can use low select or high select action to change which control action, so which controller action is applied to the manipulated variable. So override select controls can also use what's called select action to switch between manipulated variables or manipulated variables that have the same control action. So what I want you to do is, for now, I want you to review example 13.4.4 and discuss how this might work. Okay, so I'm going to summarize. We talked about low select and high select control, but not select control. So select control is a type of control that will select between a manipulated variable depending on a process reaching a constraint. This example right here talks about a distillation column. And I'll summarize, and I want you to think about this and look at about how it's going to work and how the parameters change when the process gets to its process constraint. Select control could be useful on a distillation column when your main manipulated variable is going to be the flow rate of steam to the boiler at the bottom of the column. Now imagine that the feed to the column increases such that you max out your steam heating rate or steam flow at the bottom of the column. If the valve that controls the steam flow saturates or maximizes and the flow rate continues to increase, there's nothing else you can do to get your system operating at its set point. In that case, what you would need to do is change from using the steam flow rate as the manipulated variable to the flow into the column as the manipulated variable. In other words, when the flow rate of steam saturates, you'll have to decrease the flow rate going to the column in order to keep your process at its specified value. We'll do that example next time and discuss how that works. But I want you to think about that beforehand. This is a really important example. All right. Finally, last but not least, is computed manipulative variable control. So this is going to be the last implementation of PID control that we can use to improve process performance. And this is used when the desired manipulative variable, for example, heat input, is not directly controllable. So, for example, if the heating input's just going to be the flow rate of steam, where we know the heat is equal to flow times, the heat of evaporation or heat of condensation, we know that we can measure the heating rate directly, or we can set it based on the flow rate of steam. If it's based on something else, something that might have a change in temperature, change in some property, we might need to measure multiple parameters in order to control the system. So it computes the control set point. So computed manipulative variable computes control set point from multiple measurements and from process knowledge. So again, we'll measure multiple parameters. We might have to use other types of constants or information about the system to calculate something. And this can reduce the effect of certain types of disturbances and provide better control than if we base the feedback control loop on the measurement of a single parameter. Okay, again, we'll do another example of this next time, but let's just look at one here. So here's an example of computed reboiler duty control. Okay, so here's an example where we're using quench water. So we're using quench water to heat a distillation column. So we have quench water flowing through the system. Okay, so the heating rate that's going to come from quench water, right? So quench water could have a different entering. It's going to have the temperature of the quench water can vary, which means the temperature of the quench water coming out of the boiler is going to also vary, right? And in this case, if we simply set the flow rate of quench water, we don't know what the delta T, we don't know the delta T through the system, so we don't really know the heating rate. Okay, we can get a better measure of the performance. We could simply just vary the flow rate of the quench water to keep this at or to keep the system operating at its specified value. But as the temperature of this quench water changes, the temperature of the system is going to continuously change. Okay, so if instead of just basing this on the measurement of the flow rate of the quench water, if we incorporate the flow rate or the temperatures of the quench water entering and exiting the boiler, we can achieve better control. So in this case, our composition controller would give us a remote set point that's a heating rate. So we have a heating rate, and then we can calculate the specified heating rate based on what we need to the system. When we just use steam, the heating rate is the flow rate of steam times the heat of vaporization, right? So there's no other measurements that are needed other than the flow rate of steam. And here, the flow rate of the quench water depends on these two parameters, or the amount of heating depends on these two temperatures as well, right? So we can say that Q, the amount of heating, equals F. So Q specified equals F times Cp delta T, so T in minus T out. And in here, we can set this flow rate based on these temperatures coming in and temperatures coming out and the specified heating rate. Okay, so main difference here is that we require the measurement of multiple parameters to achieve better feedback control than we could achieve based on a single measurement. Okay, so let's wrap this up a little bit. We have a few things that we talked about. We said inferential control can be used to reduce dead time or measurement lag, and it's also going to have advantages in cost and reliability. And the main thing you need to know about inferential control is you're using the knowledge or correlation between two variables to control using easy and cheap measurement methods like temperature, pressure, flow. Scheduled or adaptive controller tuning can reduce the effects of process nonlinearity. So this is going to make our system more reliable. Because again, a system that's nonlinear, that's subject to large disturbances, can have reliability issues. Using adaptive controller tuning is we can change the values of the PID parameters based on the measurement of a specific value, such as the flow rate entering the system. OverrideSelect controls. We're going to do some examples of this next time. These are used to make sure our system doesn't go outside of safety constraints, or that our system doesn't reach the operational constraints, like full level in the tank, or the tank empties, for example. And for reactor systems, we can maintain temperature so systems don't run away or equipment doesn't fail. And finally, as we just mentioned, computed manipulative variable, we can reduce the effect of specific disturbances, like the temperature of the quench water. And we also achieve much better control in the system, and we subject our process to less variability by having a better measure of what we're trying to control, like heating rate, in a given process. All right, so that's going to be all for today. We'll see you next time.